Quadratic functions are used very often to model real-life situations because gravity acts upon objects to make them travel in space according to a quadratic function. When I give you a situation that's a real-life situation, you can use this format to write the equation yourself. So if I give you this information, which just as a warning is usually not realistic, I just make up numbers. So don't think that I'm picking realistic velocities. But anyway, a cannonball is shot from a 1.5 foot tall cannon. It is shot into the air with an upward velocity of 40 feet per second. So the way that gravity works is always pulling objects to the ground with an acceleration due to gravity of negative 16 feet per second squared. So you're always going to have a coefficient in front of the x squared term of negative 16. And that, again, is how fast the object is pulled to the earth, the acceleration due to gravity. Then you can fill in the rest of this information based on what the problem gives you. So the initial velocity, the initial upward velocity is given to you, and in this case it's 40 feet per second. And then I would multiply that by my x, just by how long the object is in the air. And then my initial height gives me the constant, which is 1.5. So again, these are going to be really crazy, unrealistic situations, but we're going to write an equation from them. This part's realistic. Gravity is always negative 16 feet per second squared times x squared. Initial velocity goes in front of the x, and the starting height goes here. So for example, a ball is thrown from the top of a 20-foot tall hill. That's going to be my initial height, with initial upward velocity of 70 feet per second squared. That's going to be my initial velocity. So f of x is negative 16x squared plus 70x plus 20. In terms of finding information about the path of the object, the y-intercept is given to us in the problem. It is shot from a 1.5 foot tall cannon. So the y-intercept is given to us in the problem, 1.5. Here it is 20. Here's a different situation. A coin is dropped. So if something is dropped, there is no initial upward velocity. So v of 0 is 0. This term does not exist in this function rule. So I just have negative 16x squared plus my initial height. Sometimes I won't have an initial height because I'll be starting on the ground, and that would mean my y-intercept is 0, 0. My function rule is just negative 16x squared plus the initial velocity term. So always negative 16x squared. Sometimes there's no initial velocity if we just drop it, and then we just have the constant for the initial height. Sometimes we start from the ground, so there's no initial height, it's just 0, and we just have the term indicating initial upward velocity. To find the vertex, we can use our calculator. We can make a table and scroll until we see the y value getting bigger and then smaller. Also, we could use algebra. We could use opposite of b over 2a to find when. These directions say to use a calculator, but we will also be asked to do it by hand on a test. So when does it reach its maximum height? That's the x value of the vertex. And what is the ball's maximum height? You will plug in whatever you get here. Say you get x equals 5. We'll plug that into the function rule and find out the ball's maximum height. When the coin reaches the ground, that is not something we will learn how to do by hand in this unit. You will use the table in your calculator, and you will find what is the x value when the y value, the height, is 0. When is the football 30 feet high? This also, you would need to look at the table in your calculator, and this is one where you want to be careful and see if there's two different x values with a height of 30. Another sort of question you could be asked is, how high is the ball after 1 second? That would be asking you to evaluate the rule for x equals 1, for example. So you would plug in 1 to your function rule. Let's use this one. And this will tell me how high my cannonball is after 1 second, evaluating that function rule for 1.